now admitting everyone to join. Okay, hello everyone and welcome to the second day of Prague Summer School. Before we start with Subhash's second lecture on hardness of approximation, let me just make one short announcement, or actually two. First, there was a typo in one of the homework assignments, so there is a correction on the web page. And second, in Subhash's set of exercises in the first set, problem number 5 had two parts. The first was fairly routine, I believe, but the second one required some knowledge about random walks on expanders. So Vašek Rozhoň of ETH agreed to give sort of an informal tutorial on that, and that will be tomorrow at 12:30 UTC, so 90 minutes prior to Subhash's lecture, and will take around 60 minutes. So there will be instructions on the website. It will be broadcasted on YouTube as well. So if you want, please join tomorrow at 12:30 UTC. Okay, and now it's my pleasure to welcome Subhash, and we can start with the second lecture in his series.
Okay, so all right. So today I will be covering this well-known result of Johann Hofstad called 3-bit PCP. So this states that we have PCPs that make 3 queries to the proof. The predicate is linear, and the completeness and soundness are 1 minus epsilon and half plus epsilon. So if you interpret as a hardness result for linear equations with 3 variables, then it says that it's NP hard to distinguish whether the optimum is at least 1 minus epsilon or is at most half plus epsilon. And as I remarked, this half here is optimal. And also this 1 minus epsilon here, which is imperfect completeness, so to speak, that's inherent, right? It's necessary. And and this PCP at a very high level, you can think of as composition or combination of 2 modules. One is a purely combinatorial module called dictatorship testing, and another one is the hardness result for a problem known as label cover. And you will see the whole entire proof. It will have many parts, right? And slowly, hopefully, we will build all the parts one by one and then put them all together. I mean, you might get a bit lost, right? To be fair, but I do hope to cover all the parts, put them together, but leaving out some proofs and some of the proofs which you are actually supposed to read beforehand. But in any case, all the notes are written and video is recorded. Okay, so yeah, so we did this last time, but quickly recall. So label cover is this, well, unfortunately cumbersome looking problem. So it's a labeling problem with underlying bipartite graph. The goal is to assign labels to vertices to both left-hand side and right-hand side. The right-hand side is thought of as larger in some sense. And the labels are supposed to be from integers 1 through capital M for the right-hand side, from integers 1 through capital N for the left-hand side. And the edges are given by constraints, and the constraints are specified by projection maps pi, which are just maps from M to N. And the intention is to find a labeling, and a labeling is said to satisfy an edge or a constraint on, let's say, little v, little w, if the label of w maps to the label of v according to this map pi. Okay? And of course, the goal is to find a labeling that satisfies maximum fraction of edges. And there is this quick reduction from gap3 sat where we use PCP theorem, which shows that for this problem, it's hard to distinguish whether the optimum is 1, meaning a perfectly satisfying labeling, versus the optimum is at most alpha. Let's say alpha equals 0.99. And this, for this, it's enough to have 2 labels on left-hand side and 7 labels on the right-hand side. This is a concrete reduction. Yeah, and then turns out you can amplify this gap by as much as you want using this product construction called parallel repetition. And here I show it pictorially. Let me skip, formal description. And it should be self-evident what this construction amounts to. So this is the label cover instance, the original one, so to speak, on the left-hand side. Call it L, and then you can construct an instance L to the kth power. So this is the k-wise product, and think of k as a large constant, like 1,000. And it simply amounts to making tuples, right? So on the left-hand side, the new vertices will be k tuples of the old vertices, right? So typical vertex here would be v1, v2 up to v sub k. On the right-hand side, a typical vertex would be w1, w2, w sub k, where all these vi's and wi's are original vertices, right? And naturally, you put an edge between 2 tuples if there was an edge in the original instance between v1, w1, v2, w2, up to vk, wk, right? And then the labels, again, these are product labels. If you want to assign a label to this tuple, you really need to assign a label to w1, label to w2, up to label to wk, right? And similarly to the left-hand side. And finally, what's the projection constraint? It's simply the product of the projections from the original instance, right? So if you have a labeling to this tuple and labeling to this tuple, the overall constraint or the projection map will require you to map label of w1 to label of v1, and label of wk to label of vk as per the original instance. Okay, right. So it's a perfectly natural product construction. Now it's clear that if the optimum of the original instance was 1, meaning if there was a labeling that satisfied all edges, you could just take that labeling and faithfully apply it to each coordinate, right? And you will get a labeling to this new instance with also optimum 1. Now, what is much, much harder to prove, and this is a very famous result of Raz from mid-90s, that if the optimum of the original instance is bounded away from 1, then the optimum of the new instance goes down exponentially as the number of repetitions. Okay, so of course we're not going to prove this. This is a parallel repetition theorem of Raz, right? And then then you can Right. So then applying this parallel repetition theorem, you can amplify the hardness of label cover, right? And you can get this theorem that it's NP hard to distinguish whether optimum of a label cover instance is 1 versus epsilon, where epsilon is arbitrarily small constant. Right? To reach a certain value of epsilon, you just have to take sufficiently many repetitions, the number k. And clearly, the size of the instance will increase from n to the k. Number of labels will also become exponential in k, but this will stay a constant as long as k is a constant, and the reduction will be polynomial time as long as k is a constant. Okay? So this result you want to keep in mind and keep aside, right, as one module. Okay, and we'll come back to this eventually. Okay, so then the module on the right-hand side, which is this dictatorship testing module. So this I'm assuming that you more or less already read what this is. So we will sort of do a quick overview. And for that, right, we do need some basic background in Fourier analysis. So just to quickly recall, we will be concerned with functions on the n-dimensional Boolean hypercube. And the functions will be denoted by letter capital A or capital B. And generally, we want to study real valued functions. But more specifically, we are interested in Boolean functions, meaning functions whose values are also +1, -1. And the hypercube itself is thought of as +(-1) to the n. Now, there is a special class of functions called character functions. And for every subset alpha of the indices 1 through little n, these are the coordinates, right? There is a function called chi sub alpha, which is simply the product of the bits in that set. So these are called character functions. and these are really linear functions. If you just think of them from so-called additive notation. So here we are using so-called multiplicative notation. So that's why it is a product here. Okay. The main point is that any function on the hypercube can be uniquely written as a linear combination of these character functions, right? So that this would be the so-called Fourier or Walsh representation or expansion. So the function A is simply summation A hat alpha chi sub alpha over all subsets alpha. And this A hat alpha, these are just real numbers, which are the coefficients, called the Fourier coefficients. And this fact here, this would be kind of important one, that if A is a Boolean function, then sum of squares of Fourier coefficients it's simply the so-called L2 norm of the function, squared L2 norm, which is 1 for a Boolean function. So for a Boolean function, sum of squares of Fourier coefficients is 1. That's the important fact. And therefore, if one wants, these squared Fourier coefficients can be thought of as a probability distribution over the coefficients. Okay, so that's the important point. And the Fourier coefficients are related to distance of a function from Hamming distance of a function from the corresponding character. But this is not going to be very central for this talk, but you can read it if you want. So let's skip this. Right, and now let's move to the linearity testing problem. Now, this linearity testing problem, well, it's an important problem in itself, but what we really care about is the dictatorship testing problem. And so the linearity testing is sort of just a warm-up, okay, towards the dictatorship testing problem. So as I said, let's stick to multiplicative notation. So these chi alphas, these are really the class of linear functions. And this is really the definition of linearity. But for every inputs x and y, chi alpha x times chi alpha y equals chi alpha xy, where xy is an input which is which is simply product of the coordinate-wise inputs x and y. Okay, so I hope this is clear. And this is really definition of linearity. This is what is meant by linearity. Okay. Right, and yeah, let's just focus on this bottom part here. So the linearity testing problem is the following: that you are given a function a, or in the PCP literature, these are sometimes also referred to as tables. So if I say function or a table is the same thing. So given a function a, Boolean function, your goal is to test whether a function is linear. And you want to do this testing, in this case, using just 3 queries. Okay, so you want to look at 3 values of the function, and it's a probabilistic test, accept or reject, and then you need to have completeness and soundness properties. Okay. So what can you expect as completeness and soundness properties? So completeness usually refers to the case that if everything is fine, then everything is fine. Okay, so this is usually easy. So in this case, if a function is indeed linear, meaning if it's a character function, then the test accepts with probability 1. Now soundness. So here the conclusion is you can draw up different conclusions depending on what you really need. You can even make different definitions. And whenever one makes a definition, usually the question is, what is the definition good for, right? So I'm going to make certain definitions. And of course, the intention is, what is it good for? So the application will come later. Okay. But from a high level point of view, the soundness property typically, one wants to show that if a function is far from being linear, in this case, then the acceptance probability is far from 1. Okay, so that's the rough conclusion, and we'll see more specific conclusions when we actually look at the test and the analysis. And here is a linearity test. This was already studied by Blum, Luby, Rubinfeld, right? Even prior to actually even the PCP theorem in early 90s. And it's a 3-query test, and it's a perfectly natural test. So as I said, forget this thing about Hamming distances. We are really not going to use Hamming distances here. But the test itself is very natural, right? So by definition, a function a is linear if a of xy is a of x times a of y. So if you want to test whether a function is linear, so naturally, one thing you could do is pick x and y uniformly at random, right? And then read the bit a of x, read the bit a of y, and read the bit a of xy, right? XY is just another input. If you want to call it Z, then call it Z, right? So this is the test. Now, clearly, you are making only 3 queries to the function. It does have perfect completeness, meaning if the function is indeed linear, of course, by definition, the test passes with probability 1. Okay. So what you are left with only is the soundness conclusion. So what is the soundness conclusion you can draw? Right. And here is the really marvelous trick. I mean, it's such a easy thing, but you know, in hindsight, it's a really marvelous trick that you can express the acceptance probability of the test as what is called as arithmetized predicate. Okay, so you can write it as expected value of the choice of the pair x and y. This expression 1 plus ax, ay, a of xy divided by 2. Okay, and just to be sure we understand why this is, all these are plus minus 1, right? And the test accepts if a of x, a of y equals a of xy, in which case this whole product is plus 1, and you get 1 plus 1 over 2, which is 1. If the test rejects, this product is minus 1, and you get 1 minus 1 over 2, which is 0, right? So this expression is 1 or 0, depending on whether the test is accepted or not, and therefore the test acceptance probability is the expectation of this expression. Okay, I hope that was clear. And once you write this, now it's some sort of routine Fourier manipulations, right? And you were already supposed to read these manipulations, so I'm not going to go them line by line, right? So you write it as simplify this expectation. Now plug in the actual Fourier representation of the table or a function A, right? So I'm expressing the A in terms of its Fourier coefficients, do some rather elementary manipulations. But if you are never used to it, I highly recommend going really line by line, and you will see the magic of Fourier analysis. And this is even very elementary Fourier analysis. Okay, and what it eventually gives you is that the probability of acceptance is this expression, which is half plus half, and more importantly, sum of cubes of Fourier coefficients. Okay, this is what is important. You get cubes here and not the squares. Okay, and now the conclusion we want to draw is the following: that if the acceptance probability is half plus epsilon, right? Think of epsilon as small constant. What can you conclude? Okay, now clearly, if this expression is half plus epsilon, then it amounts to saying that sum of cubes of the Fourier coefficients is at least epsilon or 2 epsilon. It really doesn't matter. Okay. So that's what I will just focus on the conclusion here, which appears in the last line, that if the acceptance probability is half plus epsilon, then sum of cubes of coefficients is epsilon. But we know that for a Boolean function, sum of squares is 1, right? So if sum of cubes is epsilon, then it must be the case that the maximum among them in magnitude must be at least epsilon in magnitude, right? Yeah, so I hope this is completely self-evident, right? And you get this only because you got the cubes, lower bound on the cubes of the sum of cubes. Okay, so what the conclusion is saying is, if the acceptance probability is half plus epsilon, then there is some alpha such that the corresponding Fourier coefficient is large in magnitude, right? So half plus epsilon acceptance gives a large Fourier coefficient. Okay, so this is what you want to somehow, right, hardwire in your mind. You get large Fourier coefficients. Okay, so now let's move on to the real thing, which is called the dictatorship testing. Now again, you might wonder, right? Why do we care about linear functions? Why do we care about dictatorship functions? Again, right? The answer is always, what is it good for? And the answer will eventually come later, right? These are really good objects to study as far as PCPs and hardness of approximation is concerned. Okay. I mean, you might want to study dictatorships for other reasons as well, but right. So dictatorship functions, these are very, very special class of functions. In fact, there are exactly n of them, one for each coordinate. So for every fixed coordinate I from 1 through n, the dictatorship function is simply, the value of the function is simply the ith coordinate x sub I. Okay. Or alternately, you can think of it as a character function, but it's a character of a singleton set. Okay. So there are exactly n of them. And you want to, the testing problem is the same, right? You are given a function and you want to test whether it's a dictator. In this case, we still want a 3-query test, which is linear, meaning your test should pick 3 inputs x, y, z and test whether a of x, a of y, a of z is plus 1. You want good completeness, meaning if a function is indeed a dictator, then the test should accept with probability, well, ideally 1, but in this case, we will necessarily have to settle for 1 minus epsilon, the imperfect completeness, which is again necessary here. And then the soundness, that if the test accepts with probability, let's say half plus epsilon, then what can you conclude, right? So ideally, you should be able to conclude that if it's half plus epsilon, then the given function A resembles a dictatorship. Okay, whatever this word resembles means, that you will have to define, right? And again, why this particular definition? Because it's useful, right? That's always the answer. So what do I mean by resembling a dictator? Okay. Okay, so that's the next slide. So obviously a function is a dictator if by definition it's a character chi sub alpha, where alpha has cardinality 1. Okay, and in particular, if it's a Fourier character itself, then that particular Fourier coefficient is 1 and all other Fourier coefficients are 0. Okay, so it has a large Fourier coefficient of small cardinality. Okay, right? And then I start calling a function as a resembling a dictator if it resembles this characterization. I mean, I will loosen it by allowing to have large Fourier coefficient, but still at least some little delta in magnitude, and having some bounded cardinality. Okay, so this is the definition. A function is delta h junta. I'm lying here a little bit. In the literature, the word junta is used for something related, but a little bit different. So this definition is just for the sake of this set of lectures. So I will call a function delta h junta if there is a Fourier coefficient alpha, which is large in magnitude, meaning its value is at least delta in magnitude, and the cardinality is bounded. Its cardinality is at most h. So think of delta as 1 over 100 and h as 100. So if there is a Fourier coefficient which is at least 1 over 100 in magnitude, but at most 100 in cardinality. Okay, and then this is thought of as a relaxed or looser version of what a dictator is. Okay, so clearly dictator is a 1-1 junta. So I allow it to be delta h junta. Okay, and that's what I meant by resembling a dictator. Okay, and then we want to design a dictatorship test, which Hostad already did. So here is a specific statement of his result, that there is a 3-query linear test, which has this completeness property that if a function is dictator, then it accepts with probability 1 minus epsilon, and more importantly, if the test accepts with probability little more than half, so let's call it half plus eta, then the function is indeed a junta. There is some quantitative dependence on these etas and epsilons, but don't worry about this particular dependence. It will come out of the proof, but nothing is really going to depend on what this precise dependence is. So I'm just going to ignore even saying what this dependence is. All that really matters is that all these dependencies are purely on epsilon and eta and not on n, which is the dimension of the hypercube. Okay, that's all that really matters. Okay, so now what is this test? Now it's natural that you simply want to start with the linearity test, a of x, a of y, a of xy. But then linearity test will pass all the linear functions, right? But we only want let the dictatorships pass safely, right? Because dictatorships are even much more smaller subclass of the linear functions. So we only want the dictatorship to pass. On the other hand, we want, if you have a linear function of large cardinality, we want to kill it somehow, right? Yeah, so we want a mechanism to punish large cardinality characters. And in hindsight, the solution is sort of obvious, but right. But when it came, this was really like a genius solution. I mean, it still is. Yeah, the trick is to add noise. Okay, so what do I mean by this? Yeah, in fact, I can even describe here immediately. So it's the same test: a of x, a of y, a of xy. Except that what you do is you pick one of the 3 inputs, x, y, and let's call this third input z. Z equals xy. So you pick any one of the 3. Let's say I pick z for the sake of concreteness, and then flip every coordinate of z independently with probability epsilon. Okay, so I just take a noisy version of Z, and that's it, and that's the test. Okay, right. So yeah, so this is the test. Picks xy uniformly at random and accept if and only if a of xy mu equals ax times ay. This is just a different notation. So mu just refers to this additional noise. Okay, so I mean, here is a formal definition which you can look at later, but all it amounts to is I'm flipping every coordinate of xy with probability epsilon and independently. Okay, that's the noise. So I just added noise and that's it. So it's a noisy version of the standard linearity test. Okay, right. And now we do the same analysis. Again, you were already supposed to read this, but even if you didn't, no matter. This is what the conclusion you are eventually going to get. So without the noise, recall that the acceptance probability turned out to be half plus half sum of cubes of Fourier coefficients. Now you pretty much get the same thing, except that with every Fourier coefficient alpha, so recall that alpha is a subset of the n coordinates, right? So you get this so-called damping factor, 1 minus 2 epsilon to the size of alpha, right? Which really essentially becomes 0 as alpha, the size of alpha increases. And this is what is meant by, I meant by punishing the large characters, okay? And now it's clear that if the test of acceptance probability is half plus eta, let's say, then this expression here on the right-hand side, this has to be at least eta, okay? Right, this sum has to be at least eta. Again, sum of squares of Fourier coefficients is 1. So at least one of the term must be at least eta, meaning there is some alpha for which this whatever is left out here, once you take out the square, which is the coefficient a hat alpha itself, well, there should be hats everywhere because these are Fourier coefficients. The coefficient a hat alpha should be large, plus this damping factor should also be large, which means the size of alpha has to be bounded. Okay, so this is what the conclusion you are going to get, that if this test with noise accepts with probability half plus epsilon, sorry, then there is a Fourier coefficient alpha naught, which is large in magnitude, in this case at least 2 times eta. But as I said, this quantitative dependence I'm not really going to care so much. And moreover, the size of alpha naught should itself be, the cardinality should be bounded, okay? And therefore the function must be a junta with those parameters, right? And that's the, this is the conclusion of the dictatorship test. So again, keep this dictatorship test again aside, right? So I'm just building these modules one by one, and eventually there is going to be this aha, right? You put everything together. Okay, and just as a side comment, the way these dictatorship functions are useful in the PCP context is these are really thought of as encoding schemes. So imagine that you want to encode an integer from 1 through n. So, so what you could do is you could take the dictatorship function of that number, the coordinate I between 1 through n, and write down the entire truth table of that dictatorship function. Okay, table of values of the dictatorship of the ith coordinate. And think of it as an encoding scheme, encoding an integer from 1 through n using this enormous string of length 2 to the n. Well, 2 to the n because it's the length of the truth table. Now, clearly this is completely ridiculous from the standard coding theoretic point of view, where, right, you want really efficient length codes. If you want to encode an integer from 1 through n, the coding theorists would insist that you have to do it within bits, which is, let's say, something like constant times log n bits, right? But here you would be using 2 to the n bits. So this is completely ridiculous from coding theory perspective, but it is extremely useful from the PCP hardness perspective. Okay, and then to recall, we already covered this label cover hardness. We covered dictatorship test module. Now we will put them together to do the composition. Okay, so what I want to do is first give this general sense of what this composition is. Okay, and then first give general sense. Then we describe yet another module, okay, and then do the final thing. Okay, and hopefully we will do everything in time. Right. Okay, so this is the end of this. All right. Okay, so again, this is sort of again overview how we intend to do this, do the final thing. So to recall, this is the instance of label cover, right? And it's a hard instance of label cover, meaning it's NP hard to tell whether the optimum is 1, meaning there is a perfect labeling, or the optimum is at most some constant, little constant delta, right? So this is what we did, showed that this is NP hard using PCP theorem and this so-called parallel repetition theorem. Okay, and just to recall, you have vertices, labels, and these projection maps. Okay, now this, once you have hardness of label cover, I mean, this itself you can think of as a PCP of sorts, right? Where you can demand to the prover or the adversary to give you a labeling to this instance, right? So the prover or the adversary just writes down labels to both vertices to the left and to the right, right? Meaning for every vertex to the left, the prover writes down an integer, right, from 1 through capital N. For every vertex on the right, the prover writes down an integer from 1 through M, which are supposed to be the labels. Okay, and then you, as a verifier, simply pick an edge VW at random, read the labels of at the V and the W, and accept if they satisfy this constraint that pi of the label of W is equal to label of V. Okay, so this itself is a PCP, really. Okay, and this is a PCP with 2 queries, right? You just read 2 labels, one for V, one for W, except that what you read are these integers. I mean, they're of constant size, but still large integers. Okay, so your queries are non-Boolean. Okay, and you have perfect completeness and soundness of at most delta, because in the no case, there is no labeling satisfies more than delta fraction of the edges, right? So the soundness delta. So this is all great, except that my queries are these huge, huge sized queries, not bits. But eventually, right, we want a PCP which has 3 Boolean queries, right? I mean, that's the Hasta 3-bit PCP. So how are we going to achieve Boolean queries? And then here is the key idea, which is very prominent in all PCP literature, called the proof composition. Okay, and if there is one idea I want to take you from this lecture is really this one. Okay, and this is a trick which is used over and over and over again. And the trick is, whenever you have some PCP that you already constructed, in this case, just demanding the labels, that itself is a PCP. So you take your PCP, and then instead of answers or labels, okay, in this case labels, decide on some a priori encoding scheme and ask the prover, tell the prover, look, instead of giving me an answer or label in this case, give me an encoding of that label, okay, using whatever encoding scheme I propose. Okay, and that's it. This is the trick which is used over and over again. Now, in this case, the encoding scheme will be the long code, which we talked about. And just to recall, the labels are supposed to be integers for the left-hand side between 1 through capital N, for the right-hand side 1 through capital M. And now the verifier is demanding to have labels, long codes of these labels. Okay, and let enc V and enc W be these supposed long codes or long codes of these labels. And then the verifier is going to run some tests on these encodings to test whatever he or she needs to test. Okay, so let's even specifically say what needs to be done. So of course, there is this underlying label cover instance. Now the verifier is saying, look, for every vertex little v or little w of the underlying label cover, right? So the label cover instance is always sitting there, right, in the background, right, implicitly. So for every vertex v or w, give me an encoding of the label of v, an encoding of the label of w, okay, using whatever encoding scheme I proposed. Okay, now this is what the proof, or this is what the prover gives you, right? This is what the return PCP proof appears to you as. These are a whole bunch of long strings, one string for every v, one string for every w. Okay, and now you are the verifier. So what do you need to check, right? So you would need to check that whatever is written here, enc v, it is indeed the long code encoding of the label of v, meaning enc v is an encoding of an integer I sub 0 between 1 through n. And more, similarly on the right hand side, that this enc w, which is some long string, it is indeed encoding of some label or integer j sub 0 between 1 through capital N. And moreover, pi of J0 equals I0, because that is the underlying constraint of the label cover itself, right? So I hope that makes sense. What is given as a proof and what needs to be verified. Okay, so what you need to verify is that these are indeed code words, okay, and not some complete garbage strings. And moreover, they encode what they encode, which are integers I0, J0. They satisfy this constraint that pi of J0 equals I0. Okay. Now, if you really think about this, this is really a tall order. This is almost impossible, incomprehensible. How are you supposed to test all this just by looking at 3 bits in the proof? Okay. And yeah, I don't know how how much one can appreciate at this point, but hopefully when you go home, look at everything together and like meditate over it. Hopefully you will see the magic. What remarkable achievement this was. Okay, and then Hastad is going to do everything in one shot, reading just 3 bits, 2 bits from right hand side and 1 bit from the left hand side. And these are 2 separate, you can think of this as 2 separate tasks. First, checking that these are actually code words, and then that they encode, what they encode satisfies this pi condition called code word test and consistency test. But then Hastad is going to combine both, do everything in one shot, okay, with 3 queries. All right, so that's the high level framework. And now come the actual details. But I would think that even if you followed till this point, I would consider my job done. But we do have like fair bit of time, so I will describe the entire construction as well. Yeah, but from here onwards, if you just completely lose me, it won't be, it won't be perfectly fair. All right. Okay. So yeah, so now this gets a bit messy. So let's think of this as a separate module, right? Because this is what we want to test eventually, that we have 2 encodings, well, supposed encodings, one on left-hand side, one on right-hand side, right? And we want to test that they do encode integers I0, J0, such that pi of J0 equals I0. So this task, let's isolate it as a module and just study that module, okay? Right, so this is the isolated module that you are given 2 functions, A and B. So A is a function from plus minus 1 to the n to plus minus 1. So here I'm using little n and little n. If you want to correspond to what we said before, this should really be capital N and capital M, right? These labels on the 2 sides. And these are really supposed to be long code encodings of labels, right? So A and B, these are supposed to be long codes of the label of A and label of B. So the label of A is supposed to be an integer, I0, from 1 through little n. And therefore, A is a function on plus minus 1 to the n to plus minus 1, which is really supposed to be, ideally speaking, or in the honest case, the dictatorship of the I0 coordinate, right? So the singleton character chi sub I0. And B is supposed to be then the true long code encoding or dictatorship of the coordinate J sub 0, right? Between 1 through little m. And moreover, pi of J0 should be I0, okay? So you want to test all these 3 things in one shot, okay? By making 2 queries to the table B and 1 query to the table A, okay? And actually, it would be too technical to, in fact, actually describe what all the details of the test are. So I'm actually not going to do it, but they all appear there, and I highly recommend taking a look. Maybe not now, but maybe after the summer school is over, if it really interests you. But one simplifying thing to keep in mind, if you pretend that you are in a very simplified scenario, that m equals n, right? And moreover, this pi is just identity map, meaning all you want to check is that both A and B encode the same integer, and more or less that integer is the same on both sides, okay? If you consider this simplified scenario, and let's even say the 2 tables A and B are the same, then this is really same as the dictatorship testing, okay? You can convince yourself. And in that case, we know, right, that if the test accepts with probability half plus say eta, then the table A must have large Fourier coefficient of bounded cardinality. Okay, so the conclusion that we'll get here, this is a more general setting, right? That you have two codes, A and B, and you want to test the so-called consistency between the two sides. So you are going to get a more complicated conclusion, which I will write on the next slide. So this is really the conclusion that you get, that there is a 3-bit test on, this is called 3-bit consistency test on tables A, B, and with underlying projection pi, which reads 1 bit from A, 2 bits from B. If everything is as it should be, right? So this is the completeness case, that if A and B are dictators of I0, J0, with pi of J0 is I0, then the test accepts with probability 1 minus epsilon. And more importantly, if the test accepts with probability slightly less than half, then you can conclude something, okay? And what I wrote here, of course, I mean, it's a bit difficult to appreciate what this even means. But think of it as, I'm trying to say that something similar to what ought to be the case must be the case, okay? So some loose conclusion, but even if it's a loose conclusion, it's going to be useful, right, towards the final analysis. So specifically, if you stare at closely, what you're saying is, you have two tables, A and B, one on left, one on right. Then, first of all, you have to look at Fourier coefficients. And this sum is at least some eta squared. So, and this sum is over Fourier coefficients B hat beta squareds. These are Fourier coefficients of the right hand side. A hat alpha squareds. These are Fourier coefficients of the left hand side. And this sum runs only over sets of bounded size, because right, this is sort of what dictatorship test wants me to do, right? I have to conclude something about existence of Fourier coefficients of bounded cardinality. So these are indeed of bounded cardinality. And moreover, the two sides, A and B, they are consistent or connected, right? Related to each other in some loose sense. And more precisely, this is captured by this extra condition that this sum runs only over those pairs alpha and beta. Right. If there was no this constraint, if alpha was completely unrelated to beta, then there will be no consistency between two sides. But here is an extra condition that alpha is contained in pi of beta, where so to recall, what is the Fourier coefficients are subsets of indices. So beta is a subset of integers 1 through m, and alpha is a subset of integers 1 through n, right? So if you have a subset beta of coordinates on the bigger side, and pi is a projection, right, from coordinates from one side to the coordinates to the other side, right? So that's the projected set of coordinates, right? And the set of coordinates alpha is contained in the projection of the set of coordinates beta. So there is some consistency between the two. So this is what you can conclude by doing, again, the Fourier analysis, but the details of how exactly everything happens, I mean, they're not difficult, but they are just a bit messy to describe. So I'm going to skip all of that, but if you're interested, you should definitely take a look. It has all the standard tricks of Fourier analysis, among which, you know, the Cauchy-Schwarz is like the breathtakingly powerful tool, though so simple, though everybody in, you know, discrete math knows this. Just using Cauchy-Schwarz, you know, you can do so many great things. Right. So that's the end of this part. And now we will come to the final construction. Right. So again, we will do everything again, starting with the framework and right, going below and below, and then right, finally analyze everything. Right, and so this is the final PCP construction, right, combining everything. So just to recall again, there is this underlying label cover instance, right, and now you already asked the prover to give you a labeling to this instance, but in the encoded format, right? So for every vertex V and W, right, on either side, now the prover has given you supposed encoding of label of V and supposed encoding of label of W, right? And these are viewed as these long bit strings, capital A and capital B, which are themselves Boolean functions, right? And there is always this pi sitting implicitly, which is a map from label set 1 through little m to the label set 1 through little m, from the bigger side or the right side to the left side. And of course, this is what is expected as a proof: long code of label of v, long codes of labels of w, and these labels being integers from 1 through n and 1 through m. Now, the test is natural, right? I mean, having said everything that I said so far, so for the label cover instance itself, what you want to do is pick a random edge, let's say little v, little w, and check that the labels are, the two labels are consistent, right? Meaning pi of the label of v equals the pi of the label of v. Pi of label of w equals label of v. But now you no longer have access to the labels themselves, right? What you have access to is the encodings of these labels, right? So pick an edge, little v, little w at random. Let a and b be these supposed long codes. And again, as we know, we have to use this, keep using this word supposed all the time. So a and b are these supposed long codes of label of v and label of w. And then you run the consistency check on this a, b with the underlying pi. Okay. And this consistency check was the module that I described just before, which gives this complicated conclusion about consistency between the two tables, capital A and capital B on the two sides in terms of Fourier coefficients, right? Okay, and that's the PCP. Okay. Well, I mean, I sort of implicitly said, but let me specifically say that the test itself, the consistency test, I mean, I sort of said this, but let me emphasize, it reads 2 bits from the table B and 1 bit from the table A, and then takes and then makes a linear test on the 3 bits. Okay, and as I said, but let me emphasize again, for the sake of clarity or simplicity, you should just think of the two tables A and B as being the same and pi as just being the identity map, and the label sets on two sides M and N being just identical. In that case, it will just reduce to the dictatorship test, the noisy dictatorship test. Okay, and to recall there, it was indeed 3-bit linearity test, a 3-bit linear test, right? And therefore, the final PCP is also 3-bit linear predicate. Okay. And this is how it relates to the dictatorship test that we did before. Okay, all right. And this is the PCP. And now all we need to do is to well, make sure that we have the completeness property and make sure that we have the soundness property. Now, the completeness property, as always, is the easy part, meaning we can assume that the underlying label cover instance has optimum 1. So there is a labeling to vertices on both sides, which satisfies all edges perfectly. And therefore, as soon as you pick an edge little v, little w, everything is as it's supposed to be, right? You have the correct long codes of the two labels. Label on one side does indeed map to the label on the other side. And then we know that in this case, the consistency test did pass with probability 1 minus epsilon. Consistency test was this module, right? Which analysis we skipped. Okay, so this is fine. Now the soundness part is the real like it's almost like a stroke of a genius. So what you want to show is if the verifier accepted with probability even slightly less than more than half, say half plus eta, then well, you want to show that the acceptance probability is at most half plus eta. So we are doing the contrapositive. If it is more than half plus eta, then we reach a contradiction. Okay, and the way to reach this contradiction, and what I'm going to say in the next 2 sentences, that's really the key message here. Okay, and that's what you should try to internalize. The way to reach a contradiction is assuming that the verifier accepts with probability half plus eta. You reach a contradiction by showing that by coming up with a labeling to the label cover instance, which satisfies a good fraction of its edges. Well, good meaning there is some quantitative dependence here, which you should ignore. Okay, so satisfies some good fraction of its edges, but then a priori you could have chosen the label cover instance to have low enough soundness delta. Okay, and then that would give you a contradiction, because a priori you chose the label cover instance so that there is no labeling which satisfies more than delta fraction of the edges. Okay, and that is what would give you a contradiction. Okay, so this is the strategy, that if the verifier accepts with probability half plus eta, then it is possible to come up with a good labeling to the label cover instance. Okay, that's the strategy. And just to looking ahead a little bit. So how are you even going to come up with a labeling, right? So let's say, for the sake of argument, that you have this vertex V here, and you have this some Boolean function called capital A, right? Now, this is all you have access to, some Boolean function. Now, how are you going to come up with a labeling to this vertex V, given the Boolean function? Meaning, you want to decode somehow decode a Boolean function and come up with one of its n coordinates, right? So it's a Boolean function of n coordinates. So what you want to do is you want to stare at a Boolean function on n coordinates and somehow pick one of the n coordinates in some manner, in some meaningful manner. Okay, so that's the decoding task. So even if you try to think about this, independently, as just as a thought experiment, this will already be quite illuminating, right? So, right, this is thing. Forget everything I said throughout the lecture. Just think of this as thought experiment. You want to stare at a Boolean function on n coordinates, okay, and somehow pick one of the n coordinates as being special, okay, in some meaningful manner. Okay? How are you going to do it? Just think of this as, right, independent exercise, and that should already be quite instructive exercise. Right, and this generally, in more general terms, is referred to as decoding, right? Okay, and then in this case, this decoding would really amount to coming up with a labeling to the label cover instance. Okay, and we will see how it is going to work in this particular case. You are going to look at Fourier coefficients. That's the short answer. Okay, but in any case, let's do step by step. So we start with the assumption that the verifier accepted with probability half plus eta. Okay. Now note that the verifier itself, it involved two steps, right? First picking an edge, VW, and then doing something specific to that edge, right? Meaning on that two tables A and B associated with the endpoints of that edge. So it's really a two-step process. Pick an edge and then do the consistency test. Now, if overall you pass with probability half plus eta, then it must be the case by using what is standardly known as averaging argument, which I hope, right, for this summer school, this should be a standard terminology. By averaging argument, it must be the case for at least eta over 2 fraction of the edges. The consistency test which came later must have accepted with probability half plus eta over 2. Right? So if you never heard of this before, all I'm saying is the following, that if average score of students in the class was 52%, then at least 1% of the students must have received a score which is at least 51%. Okay, so that's all I'm saying. This is usually referred to as averaging argument. Okay, so for at least eta over 2 fraction of the edges, the consistency test must have accepted with probability at least half plus eta over 2, exceeding half. So call any such edge as good edge, and we know that for a good edge, meaning if the consistency test accepted with probability slightly more than half, then we have this conclusion from the soundness analysis of the consistency test, that there is this complicated expression involving Fourier coefficients a hat alpha square on the left hand side, b hat beta square on the right hand side, such that the sum is at least something, eta square over 4. It's not, the quantitative things don't matter so much here. Okay, and moreover, that the size of beta is bounded, cardinality of beta is bounded, and alpha as a set of coordinates is contained in the projection of the set of coordinates beta. Right, so this is what is consistency. Alpha is contained in pi beta. Okay, now just keep this expression, just keep staring at it, And I mean, presumably Hastad stared at it enough, and then almost like as a stroke of genius, came up with the following decoding scheme. Okay, how to now extract or decode and actually labeling from this. Okay, and this is the scheme. So suppose you have the vertex V, and for that vertex, all we have is this Boolean function, right? Capital A. Now, from this Boolean function, I want to decode it as some one particular coordinate. Okay, and what Hastad proposed is this is how I'm going to decode, and the decoding itself is actually probabilistic or randomized. We know that for Boolean function, sum of squares of Fourier coefficients is 1. So I could pick a Fourier coefficient alpha, which is a subset of n, with probability which is a hat alpha square. Okay, so this is a probabilistic. So pick alpha with probability a hat alpha square. Now alpha is a set of coordinates, subset of coordinates. So pick one coordinate from alpha at random. So pick a random index or integer I from alpha. Okay, and this I will be defined as the label of the vertex V. Okay, so this is what the decoding, probabilistic decoding is. And similarly, you do the same thing for the right hand side. So for vertex W, all you have is access to this Boolean function called B. Now pick Fourier coefficient beta with probability B hat beta square, and then pick a random coordinate or index or integer J from the set of coordinates beta. Okay, and then define it to be the label of B. Right. So this is a way of coming up with a labeling to the label cover instance, given these encodings or Boolean functions. Okay. Right. And now we will show that this labeling that we came up with is good in the sense that it satisfies a lot of edges of the label cover instance. I mean, it's a probabilistic labeling, but right, for every probabilistic labeling, there is always a deterministic labeling, which is as good, a concrete specific labeling. Okay, this is just a standard fact about expectations. So let's skip. It's an important side point, but we are running out of time, so let's skip this. Yeah, and at this point, even if you lost me for large part, even if you somehow appreciate what this labeling is doing, right? Yeah, that would be really nice, right? So how can you stare at a Boolean function and come up with a spatial coordinate? Okay, and this is what Hastad is proposing. Pick a Fourier coefficient alpha with probability, which is the squared value of that Fourier coefficient, and then from that set alpha, pick one coordinate at random. So it's a probabilistic decoding. Okay.
Sorry, Subhash, wouldn't there be a problem if alpha was the empty set?
Yes, yes. So it will be that's a good point. If alpha is an empty set, it will be a bit problematic. But so Hastad is going to propose additional trick just to completely avoid that scenario.
Okay, thanks.
Right. Right, and you can also just as a sanity check, you can see that if the function itself was a dictatorship function, right, then you always get that particular dictatorship coordinate. Okay, so you are indeed doing the right thing. So it's a sanity check. Okay. Okay. Now, yeah. Now, why does this encoding decoding succeed? Meaning, why does it give good labeling to the label cover? And here is an argument that, well, first of all, we are focusing on this so-called good edge, right? And good fraction of edges are good. And conditional on being good edge, we have this expression, right? So whatever this condition, call this condition number 1. So we do have this condition number 1. And it implies that with probability eta square over 4, when we do this decoding independently on both sides, with probability a hat alpha square, I pick alpha. With probability b hat beta square, I pick beta. Now, according to this expression, with probability at least eta square over 4, it does happen that size of beta is bounded and alpha is contained in pi beta, right? And therefore, with probability eta square over 4, all this thing happens. Then I go ahead and pick one index from alpha at random, let's say I0. Now, after I have picked I0, I know that alpha is contained in pi beta. So there is some J0 in beta such that pi of J0 equals I0, right? And moreover, the size of beta is bounded. So if I pick something from beta uniformly at random, I will hit on that J0, right? with some constant probability. Okay, so somehow, right, and the point is on two sides, it's being done independently, right? The table A and B, they are being decoded independently, but they are related to each other, right, because of this Fourier expression. So when you do the decoding actually does end up with a pair I0 and J0 on both sides, such that pi of J0 equals I0, okay, with good enough probability. Now, with how much probability you can analyze, right? With probability eta over 2, the edge itself was good, VW. With probability eta square over 4, this expression turned out to be true, right? This condition turned out to be true. And then once that condition turned out to be true, right, you picked I0 and then you got the J0 right with this much probability, because the set beta itself was of bounded size. And therefore you do need sets of bounded size, right? Because if this set beta was completely unbounded, if it was the whole set, then, right, you will not hit on the right J0, correct J0. So it is important that sets are bounded size. And then therefore, overall, you come up with a probabilistic labeling to the label cover instance, which satisfies, when you calculate correctly, this much fraction of the edges of the label cover. But this is a contradiction, provided you had chosen the label cover instance a priori to have low enough soundness. Okay, and that completes the proof. Done. Okay, and yeah, I hope, and of course, right, I'm not saying that right, all of you have to, have followed the whole proof completely, but I did want to give a full outline with all the proofs, most of the proofs inside, all the written notes, and the video you have, and if right, and if you're interested, you can write, you can understand the whole thing fully. And I very much hope that once you understand fully, you would see what a big accomplishment this was in mid-90s. And actually, I taught a course on PCPs, and there is already a link to the first two lectures in LaTeX on my website. And if you go a little bit below, this Hastad PCP is also fully written there. So you can also read there if you want. Right, and then to address this last point of Honza, is that, do I say correctly, Honza?
Yes. Yes.
Okay, so this last point, right, which is an important point, but it has an easy fix. So what if you get stuck with Fourier coefficient alpha, which is an empty set, right? Then you cannot pick anything from that. But then it turns out what you can do is you can simply ensure that the Fourier coefficient a hat alpha, when alpha is an empty set, is simply 0, right? In that case, you will never actually pick it probabilistically, right? Because you pick it with probability which is squared Fourier coefficient, but the value of the Fourier coefficient itself is 0. And this is simply by the following trick, which actually, again, it becomes a necessary trick, even inherently or fundamentally speaking. So what you do is you always enforce this condition that all Boolean functions that we consider are folded or odd functions, so to speak, that a of minus x is always minus of a of x. And once you do that, the empty Fourier coefficient is simply 0, because the function is a perfectly balanced function. Okay, but then how will you implement this condition in the PCP context? So in the PCP context, what happens is this amounts to saying that there is some Boolean variable called x, then there is some other Boolean variable which must be negation of this x. Okay, but you can enforce this condition by simply calling that other variable x bar the negation of x, right? Because in logic we are allowed to use a variable as well as its negation. Okay, so you can implement this. You can enforce this condition in the PCP setting as well. Or I mean, this is what you would do if it was 3-sat. If it was, but here it's even system of linear equation. So in fact, what you can do is you can call one variable x and the other variable x plus 1, right? Which is simply the Boolean, the opposite of the Boolean, right? Or minus x, whichever you want. Yeah. So once you do that, the empty Fourier coefficient is always 0, and you don't get into this issue. Effectively, another way of saying what's the effect of this trick is that if you didn't do this trick, then all your equations, if you in the additive XOR notation, your test was a plus b plus c equals 0, right? So if you did not do this trick, all your equations that in the instance that you produce will be of the type a plus b plus c equals 0, right? And then clearly this cannot be a hard instance, right? Clearly I can simply assign all the variables 0 and satisfy all the equations. So it will not be a hard problem. So what this trick will amount to is somehow it will flip half of the equations to a plus b plus c equals 1. Okay, by for some of these equations taking a negated variable than the original instead of the original variable. Okay, and then half of the equations have right hand side 0 and half of the equations have right hand side 1, as it ought to be the case. Okay, so yeah, so there are many small details like this in the whole thing, and everything is exactly the way it should be. Okay, so it's amazing, right? How everything perfectly fits together at a technical level, as well as conceptual level, as well as the highest of the abstract levels. Everything is just the way it ought to be. That's it. Okay. Yeah, and then this is my most favorite result in the PCP literature. Okay, so I will stop here.
Okay, so thank you, Subhash, for a beautiful and inspiring lecture. And we are looking forward continuation.
So I guess we'll see you tomorrow then. Bye-bye.
Okay, and for the rest of you, please don't forget we will have a talk by Cheyenne in 25 minutes or 22 minutes. Okay, bye-bye everyone.